Before we really start talking about flux and Gaussian surface and Gauss's law and really all the main topics of the chapter, we need to start by talking about symmetries. And symmetries are a very important idea in physics, really. So this is the first time we're really encountering it, but it's something that actually recurs very often in many different types of physics. So the first thing we're going to talk about here is the reason that we need symmetry is that the symmetry of our charge distribution is going to equal the symmetry of the field. So this is a conceptual shortcut to getting started. If we know what the charge distribution is, we can figure out its symmetry, and then we can figure out the symmetry of the field. We then know something about the field. On the other hand, if we know something about the symmetry of field, for instance, by explicitly seeing the field lines, that will tell us something about the symmetry of the charge distribution. So recognize in this case, we might start with field and then figure out charge distribution, or we might start with charge distribution and then figure out field. But the important thing is that we are assessing the symmetry of these. And this is something that inherently you'll need to think a little bit in 3 dimensions about, so it will be a little bit hard for me to show you just on the screen. We're going to start with a simple case, which is an infinitely long charged cylinder. So remember that we have to cut off the ends because our screen is not actually infinitely long, but the cylinder itself is. And so in this case, we would say that a charge distribution is uniform, of course. And so now we can start thinking about what is the symmetry of this object. So this is the sort of case where we're starting with a charge distribution that we know, we're figuring out its symmetry, and then we'll figure out something about the field. Now, using this is never going to give us suddenly a quantitative equation for the field, but figuring out the symmetry is usually step 1. So it's helpful to think about the types of symmetry, and we're going to think about the infinite cylinder as a case of this. Now, this is nice in that it really has many types of symmetry, so we can use this for all of them, but later we're going to talk about other types of shapes, and they don't all have all types of symmetry. So the first type of symmetry is translational symmetry, and so this is the idea of motion. So if we imagine starting at one point and then actually looking to the side, say this point is now further that way. But the cylinder really looks the same. Every spot on it looks the same. So that would be translational symmetry. An object that does not have translational symmetry would be something like a triangle, for instance. As you move to the side, it really looks different. And that's part of why it was important that this was an infinitely long cylinder, that at no point do we get to the edge. So the second type of symmetry we're talking about is rotational. And this is maybe a little more obvious, that as you rotate the cylinder around, it always looks like a cylinder. So anything that's circular is really going to have this. Now, one thing that might happen is you might have something that has a limited rotational symmetry. So in this case, if we imagine rotating at theta, theta can be anything, right? So this could be 1 degree, this could be 180 degrees. On the other hand, if we imagine something like a cube, this is going to have some rotation symmetry, right? We can take this side and rotate it around to the front. But in this case, we would have theta of 90 degrees rotational symmetry, and only around, of course, the axes through the different sides. So in some cases, you have a limited rotation, and in other cases, like the cylinder, i.e. any type of circle, you have this pure rotation, so any angle is okay. Then we have reflection. So reflection is like a mirror. So if we start imagining the top and then basically having a plane that we reflect around, now what was before on the top is now on the bottom. But again, for a cylinder, that's going to be something that's preserved. So if we go back to my triangle shape, that's the sort of case where it in fact does have a reflection symmetry. But there's of course going to be other shapes that in no way can you reflect it. There's no axis over which this is going to look the same. So in this case, this actually has another axis that we can rotate it around, we can reflect it around. So we can think about the center one. So again, different objects are going to have different types of reflection symmetry. You have to choose the correct plane. Now notice here that this was the plane containing the axis. So the axis is the center point, right? The center point. So if I looked at it edge on, this would be a circle, and the axis is in the middle. So understanding what is meant by perpendicular to the axis is important. So this is making a 90 degrees, and in this case the plane containing the axis means it can be oriented in any way but must go through the exact center. So similarly, if we think back to our cube, we have reflection planes that go through the center of every face, and I can't really draw 3D, but it's extending this way. And obviously there are other ones. We can think about a plane that's cutting through kind of the top and bottom. So there's lots of different shapes that are going to have different types of reflection. And just like rotation, it could be any angle or it could be limited ones. So make sure you understand what these different terms mean and that you start to think when you look at an object, what type of symmetry does it have? Because we're going to be using this, and so if you don't know what the words mean or you aren't very good at looking at an object and thinking about its symmetries, you're really going to struggle in this topic.